Welcome to Subatomic Tanvi.
Hi everyone.
What are we going to talk about today?
The Schrödinger wave equation.
As in, like the waves on the ocean?
Not quite. It's how the wave function of a quantum state changes over time.
The what of the what changes over what?
Okay, clearly we need to explain this in a simpler way. So imagine a tiny magic ball. So that can be in multiple places at once. So this tiny ball is just like a really small chameleon that can change color and shape to blend in with anything. So the Schrödinger wave equation is basically a map that can tell you where this ball is at a given point in time. But there's a catch. The catch is it doesn't tell you exactly where it is. It just gives you a probability of it being in different places.
Wow. Can you tell me more about them?
Of course. So there are two types of Schrödinger wave equations. The first type is the time independent Schrödinger wave equation. It basically describes that the potential energy does not change with time.
Is the other one called time dependent?
That's right, actually.
Yeah, I just guessed.
So, the time dependent Schrödinger wave equation describes how the wave function changes over time.
This information is great, but is there any way for us to actually see the equation?
Of course, but it's really complex.
Complex. Isn't that the very definition of quantum physics?
I mean, if you call subatomic particles complex, then yes.
All right. All right. Can you see the equation now?
Okay, just give me a second while I bring it up. Okay, so this is the time-dependent Schrödinger wave equation. And I told you it looks really complex, so you can really see it now. You can really see the complexity. So now let's just talk about some of the major symbols that are in this. So first, this H is the reduced Planck's constant. This V here is the potential energy function. This is the wave function. This symbol that looks kind of like a lantern here is the wave function. This T is time. And one point about time is it is not used in the time-independent Schrödinger wave equation because time-dependent, that's why it has time. Time-independent does not have time. And then moving on, the m here is the mass of the particle. And this upside down triangle-like thing is the Laplacian operator, which is used in the time-independent Schrödinger wave equation, but not in the time-dependent Schrödinger wave equation. Time-dependent has time, time-independent has the Laplacian operator. And
That's That's fascinating. A lot to take in, but fascinating. But where do we actually use this equation, like in the real world?
in the real world, quite a few places like lasers, MRI scanners, electronics, any semiconductors, and even materials science. They're all examples of things in the real world that you can use the Schrodinger's wave equation to help you with.
MRI scanners.
Yes.
That caught my brain. Can you talk about how Schrodinger's wave equation is used in MRI scanners?
Of course. So for MRI scanners, basically magnetic fields go into the human body and then they start changing the spin of the subatomic particles on the organs, like upspin to downspin or downspin to upspin. on the organs like the heart or the brain or really any organ in the human body. And since these spins of the subatomic particles are changing, it gives scientists a chance to learn more about them and learn more about the behavior of the subatomic particles, but also to understand if there's something unusual going on with the organs.
Magnetic fields, huh? So I guess that's why it's called magnetic resonance imaging.
Definitely.
That's awesome. Thank you for another phenomenal episode, Subatomic Tanvi.
You're welcome. Bye, everyone.